Okay, this is FRQ number 6 from the 2026 AP Statistics exam. It says to win a game, a baseball team needs to score runs. To score runs, players need to get on a base. The primary way players get on a base is by hitting the ball. Figure 1 shows the relationship between the number of hits and the number of runs for 30 randomly selected professional baseball teams. Okay. Part A says consider the scatter plot in Figure 1. Part 1 says describe the relationship between the number of hits and the number of runs for these baseball teams in context. And so looking at this scatter plot, I see that it's almost following a linear pattern. It is going up, so it is positive. I wouldn't say it's weak because there is more of a cluster around where the potential line will be. But I also wouldn't say it's strong. So if I was to describe this, I would say that, let's write it up here. There is a moderate, positive, linear relationship between the number of hits and the number of runs. Okay. Number 2 says, based on the data from the sample of 30 teams, an equation of the least squares regression line model for predicting the number of runs from the number of hits is as follows. Using the given regression equation, calculate the point estimate for the predicted number of runs a team will score if they were to achieve their goal of 1,250 hits. Show your work. And so for this, all we have to do is plug in the number that it gave us. And so we have predicted runs is equal to negative 372.2 plus 0.823 times 1,250. Okay, plugging that all in, we get 656.6 runs. So this is the predicted number of runs if they were to achieve their goal of 1,250 hits. Okay, this information is important because we're going to end up coming back to this later. Okay, part B says each team has a total salary equal to the sum of all salaries of all players on the team. The median total salary for the sample of 30 teams is $160 million. In Figure 2, points with dots represent teams with a total salary greater than the median, and points with squares represents the teams with total salary less than the median. Consider the scatter plot in Figure 2. Part 1. Compare the team represented by the point that is circled and labeled A with the other teams that have the same total salary classification. So since the one that is circled, A, is a square, we know that that is a group that has a salary less than the median. Okay, so in order to describe this, I would say with all teams with salary less than the median, Team A has a greater number of hits and a greater number of runs. And I can see that based on the table over here because, yes, even though this says salary less than the median, look at all the other squares. Okay, all the other ones are either to the left or are lower, which emphasizes the fact that Team A has the greatest number of hits and runs within that classification of less than the median salary. Okay, part 2 says for each salary classification, consider the linear relationship between the number of hits and the number of runs. For teams with a total salary greater than the median, is the strength of the linear relationship stronger than or weaker than or similar to the strength of a linear relationship for teams with a total salary less than the median? Okay, so for this one, we're looking at the dots and the squares, and we're trying to say which one has a stronger correlation, which one is looking more positive and more linear. And so if I was looking at that, to me, that would be the salary classification of greater than median, which is the dots. And so I would say with all teams with salary greater than median, we see a stronger linear relationship than the teams with salary less than median, since there is less scatter. Okay, part C says different types of intervals can be used when working with linear regression models. One type of interval is a confidence interval for the slope of the least squares regression line. Two other types of intervals in the context of the problem are as followed. A confidence interval that estimates the mean number of runs for all teams with a specific number of hits. A prediction interval that predicts the number of runs for a single team with a specific number of hits. All three intervals use the same basic formula, and this is what's important here, the point estimate plus or minus t star times standard error, where critical value t star comes from the t distribution that has n minus 2 degrees of freedom. The same critical value is used when finding each of these intervals with the same level of confidence. Consider the point estimate for the predicted number of runs found in Part A, Part 2, for the team whose goal is to achieve 1,250 hits next year. Recall that this value was calculated using the linear regression model based on the data from the sample of 30 teams. What is the critical value for a 95% confidence interval that would be used for the confidence interval for the mean number of runs, as well as the predicted interval for the number of runs? Indicate the answer in 2 decimal places. And so for this, what we had to do is we had to use Desmos. So let me open up Desmos. Okay, and this is a t distribution, so I would go to Add Inference, click on Probability Distribution, and click on t distribution. We said degrees of freedom is n minus 2, and our sample was 30 teams, so this is 28, 30 minus 2. Hit Create Distribution, click on the drop down, and from here we're trying to find 95% confidence interval. So I'm going to go to bounds, and I'm going to type in 0.95, and that gives me my t-star value of 2.048, which can round to 2.05. So for part I, this is the t-star value of 2.048, which is approximately 2.05. For number 2, it says the standard error for the confidence interval for the mean number of runs is 17.48. Assuming the conditions for inference are met, calculate the 95% confidence interval for the mean number of runs for all teams with 1,250 hits. Show your work. So we're using the formula that they give us above. So our point estimate is what we calculated in Part A, and that is the 656.6. Plus or minus our t-star, so 2.05, times the standard error that they gave us, 17.48. And so if we simplify that into interval form, we get 620.8 and then 692.4. Okay. Part 3 says the standard error for the prediction interval for the number of runs is 56.78. Assuming the conditions for inference are met, pretty much wants us to go through the whole process again. So the only difference here is the standard error, which instead of 17.48, Oh, I wrote too many zeros here. Hang on. So 2.05. So instead of 17.48, it's now 56.78, which gives us a new interval of 540.2 and 773. Okay. And then lastly, for part D, it says, would a distribution of sample means be expected to have more variability or less than a distribution of individual observations? And so for this, you had to know all your definitions and the connections between the two. So this would actually have less variability, and the reason for that is because mean lowers variability. And then lastly, part 2 says the standard error used in the confidence interval that estimated a mean number of runs for all teams with X hits can be found using the following formula. And then the standard error used in the prediction of interval that predicts the number of hits can be used with this following formula. So what they're saying here is that this formula was used to predict this interval, and this formula was used to predict this interval. In both standard error formulas, S is the standard deviation of the residuals, N is the sample size, and X bar is the sample mean number of hits. Based on the answer from Part D, Part 1, and the standard error formulas for the confidence interval and the prediction interval, explain why the prediction interval calculated in Part C, Part 3 is wider than the confidence interval calculated in Part C, Part 2. And so the main reason for that is if we have a high variability, we're going to have a wider confidence interval. And if you remember, in this problem, we had a variability of 56.78 compared to the other variability of 17.48. So it's much higher, which means our interval is going to be much larger. Another reason is if we look at the equation, there is an extra s squared here compared to this equation up here. So since there is an extra s squared in the formula, this is going to create a larger standard error, which is going to create a larger margin of error, which is going to, in turn, make a wider confidence interval. So that's why that interval is much wider than the previous one.